Hey folks, my name's Nathan Johnston and welcome to Lecture 5 of Introductory Linear Algebra. So remember in the previous video, we started looking at the dot product of two vectors. Well, what we're going to do in this class is we're going to start looking at the things that you can do with the dot product. Okay, and the first thing that we're going to do with the dot product is we're going to learn how to compute the length of a vector. Okay, and this just means what it sounds like. It's literally how long is the arrow that geometrically represents that vector. Okay, so let's think about this first in two-dimensional space. Okay, we'll start off there, and then we'll go on to 3 dimensions, and then we'll talk about how to do this even in higher dimensions when we can't quite picture things. All right, so let's start off in 2 dimensions. Okay, so suppose we've got some vector just with 2 entries, v1 and v2. Well, let's draw a picture, okay, to try to figure out how we could compute the length of this. And hopefully this is the type of problem that you've actually seen before, okay? We're fairly comfortable with two-dimensional geometry at this point in our education, hopefully. Okay, so we've got some vector with entries v1 and v2, and what that means is it points v1 units over in the x direction and v2 units up in the y direction. Okay, in other words, this distance here is v1, and this distance here is v2. And, well, we know a theorem from back earlier in our education that tells us how to compute the length of this hypotenuse of this right angle triangle that I've drawn, right? This is a right angle triangle. Okay, and that theorem is the Pythagorean theorem, okay? Pythagoras tells us that the length of this side here, in other words, the length of the vector v that we're interested in, well, it's just the square of this length plus the square of this length, all square rooted, okay? And that's what I've written down here, okay? This funky little notation on the left here, that's our notation for the length of a vector, okay? Whenever I write a vector v with these little double bars on its sides, that means the length of that vector, okay? And what I just argued was Pythagoras tells us the length of the vector is, well, first component squared plus second component squared, and then all square rooted. Okay, so in 2 dimensions, it's just that easy, but there's some important thing to note here, and that's, well, this formula here, another way of writing that down is you can write down in terms of the dot product if you like. In terms of the dot product, this is just the dot product of v with itself, and then square rooted, right? Because remember what the dot product does is it multiplies the first entries together, and then multiplies the second entries together, and then adds them up. And that's exactly what this is, right? First entry of v times first entry of v, well, that's v1 squared. Plus second entry of v times second entry of v, well, that's v2 squared, and then you add them up. Okay, so another way of writing this formula is the square root of v dot v. All right, well, let's move on to 3 dimensions now, okay? So we've got a formula that works in 2 dimensions. Let's ramp up, let's look at 3 dimensions. So again, same setup. Suppose we've got just some vector in 3 dimensions. So now its entries are v1, v2, and v3. Okay, and the trick that I'm going to do here to figure out what our answer is, to figure out what our formula for the length of this vector is I'm going to split up this vector into 2 pieces. And the reason for doing this is these 2 pieces, I know how to compute their lengths individually, okay? And I'm going to be able to use those sort of individual lengths to figure out the total length of the vector, okay? So here's the setup. I'm going to split up my vector into v1, v2, 0, plus 0, 0, v3. Seems like a silly thing to do at first, but here's why it's useful. Because now, if I draw a picture, okay, and again, I suck at drawing 3-dimensional pictures, so I just have a computer do it for me. All right, so if I've got this vector v1, v2, v3 that I actually care about, okay, and then I'm going to draw these 2 vectors that I've sort of split it up into the sum of. The first one is v1, v2, 0. So this vector is just living down on the xy plane, right? Okay, its z component is 0, so it's just what you get if you take this vector v that you care about and sort of squash it down onto the floor. Okay, so this is v1, v2, 0. In the x and y directions, it points the same amount as v itself, but in the z direction, it points none at all. It doesn't point up at all. Okay, and then the other vector is 0, 0, v3. So that's the one that just points straight up the amount that v points up. Okay, so I'm sort of splitting v up into these 2 components, an xy component and then a z component. Okay, and the thing to notice here is that this triangle that I've drawn here, it's actually a right angle triangle, right? If this vector is on the floor and this vector points straight up, then they're perpendicular to each other. So even though this is sort of embedded in 3-dimensional space, the Pythagorean theorem applies here because that is a right angle. Okay, so again, we can use Pythagoras to see that the length of this vector is length of this vector squared plus length of this vector squared, and then all square rooted at the end of the day. And unfortunately, we've got a little bit of a calculation that we've got to do this time to figure out what that actually gives us. But okay, writing down just what I said for now, length of the first vector squared plus length of the second vector squared, and then all square rooted. Okay, great, let's simplify that a little bit. The length of this first vector, what is that? Well, that's this vector on the floor here. And really, that's kind of just a vector in two-dimensional space, right? I mean, it's got an x component and a y component. But of course, the z component's not going to contribute anything to its length because it's not actually pointing up off the floor at all. It's just flat down on the xy plane. So we can just use our formula for the length of a vector in two-dimensional space for this first vector, okay? It's just going to be v1 squared plus v2 squared all square rooted. And then this squared is just the same as this squared copied down, okay? All right, and then the second vector, 0, 0, v3, well, how long is that? Well, you just look at the picture. Like, it doesn't have an x component. It doesn't have a y component. Its length is just whatever its z component is. In other words, its length is just v3. And, well, absolute value of v3, because we don't want negative lengths, right? If it's pointing down, then its length is absolute value of v3. All right, and then again, the squared is just copied down from up above. Okay, and then from this point, let's just simplify things a little bit because I've got a square root squared and silly things like that. So after I simplify a little bit, I just get v1 squared plus v2 squared plus v3 squared, all square rooted. And again, another way to write this is just dot product of v with itself, and then all square rooted at the end of the day, because that's exactly what's going on here. First entry of v times first entry of v, plus second entry of v times second entry of v, plus third entry of v times third entry of v. Well, that's the dot product. Okay, so the same thing really happened in both of these cases. In the two-dimensional case, the length of the vector was square root of v dot v. Then in the three-dimensional case, the length of the vector was square root of v dot v. Okay, well, we can't really apply geometric reasoning in higher dimensional cases anymore, right? If we go to 4 or 5 or 6 dimensions, I can't really draw a picture of it to convince you that this formula is right. So instead, what we do is we say that this formula here, this is the definition of the length of a vector, right? In higher dimensional cases, I mean, it's not even clear what we mean by the length of a vector if I'm talking about a vector in 7 dimensions. Okay, but now we do know what this means, okay? And what we mean by the length of a vector is just exactly this formula that we've seen a couple times now. Okay, so in 2 and 3 dimensions, we showed that this formula is true and agrees with sort of our intuition for what the length of a vector is. And now we're just defining it to be true in 4 and higher dimensions because we don't have an intrinsic understanding of what the length of a vector means in those cases, okay? So this is our definition in those cases. All right, so let's just go through a couple examples to make sure that we understand how to use this formula, okay? How do we compute the length of some vectors? All right, so let's start off in 2 dimensions. You just do exactly what we talked about. Take the entries, square them, add them up, square root at the end of the day, okay? So if our vector is 3, 4, then what you do is 3 squared plus 4 squared, and then all square rooted. Easy enough, okay? 3 squared is 9, 4 squared is 16, add them up, you get 25, square root those, you get 5, okay? So the length of this vector is 5. Okay, what about the vector cos theta, sine theta, where theta is just some angle, okay? I haven't told you what theta is. Let's compute the length of that vector in terms of theta. Okay, well, again, just plug into our formula, okay? The length of that vector w is, well, cosine theta squared plus sine theta squared. Well, I mean, that's everyone's favorite trig identity, right? Cos squared plus sine squared is 1, and then you square root that, well, it's still 1, right? Okay, so the length of this vector is 1. And if you think back to some things that hopefully you learned at some point earlier in your mathematical education, this vector is just pointing on the unit circle, right? And that's why it has length 1, okay? So this agrees with, sort of, hopefully agrees with something that you already know from earlier, right? This is the vector that points on the unit circle up an angle of theta from the positive x-axis. All right, but we can do this in 3 dimensions as well, and it's the exact same formula. You just either dot product the vector with itself and then square root, or you take the entries, square them, add them up, and then square root. Same thing. Okay, so the length of this vector x, 5 squared is 25. 1 squared is 1. Minus 4 squared is plus 16. Be really careful here. A very common first mistake that people make when doing these sorts of calculations is they would do something like minus 16 there because they see the minus here. Don't do that, okay? All of these, like, you're going to have plus signs between all of these, okay? Because you're getting all these entries squared before you add them up. And you add those up, you get 42, so then square root of 42. And I'm just going to leave that answer like that, okay? For the purposes of this course, square root of 42 is just square root of 42. If you want, you can plug that into a calculator and find out what decimal number that equals. It's some ugly thing. I don't care, okay? It's just root 42 is the answer. All right, but this formula, it even works in higher dimensions. So if I ask you what is the length of this vector here, well, even though you can't really picture that vector necessarily, right? It lives in 6-dimensional space, and we suck at picturing 6-dimensional space. We can still talk about the length of that vector. And what is it? Well, it's just the same formula again. The length of that vector is entry squared plus 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 entry squared, and then all square rooted. Okay, and again, all of the minus signs go away when you square them, and you just get plus signs in between everything, and that ends up equaling root 16, which of course is just 4. So the length of this vector here is 4. Alrighty, so hopefully we understand the definition and how to compute these things now. Let's do what we always do when we see a new mathematical formula or a new mathematical object. Let's look at what are the nice properties of that formula or object. Okay, so the thing that we introduced in this lecture was the length of a vector. Now, let's see what nice properties the length of a vector has. Okay, and geometrically, these are fairly clear. Okay, geometrically, these should not be surprising, but we'll go through a proper rigorous algebraic proof as well. All right, so suppose that you've got just some vector in n-dimensional space, don't care about the dimension, and you've got some scalar. Okay, well, property A here, what it says is if I compute the length of the scalar multiple, right, c times v, and then I compute the length, what you get is you get the same thing as if you just compute the absolute value of c times the length of v itself. In other words, you can pull scalars out of lengths as long as you remember to put absolute values around the scalars. And hopefully that makes geometric sense, right? Remember, scalar multiplication, all it's doing is it takes your vector and scales it by c, right? It just makes it c times as long. Except if c is negative, then it also reflects it down, okay? So that's why we need the absolute value here, right? Because lengths are always going to be positive. If I multiply it by -3, I don't want to have a negative length all of a sudden. So absolute value just throws away the minus sign. All right, and then property B here, again, this is fairly intuitive. The length of a vector equals 0 if and only if it's the 0 vector. Okay, so maybe the weirdest thing about this property here, maybe the newest thing really is the language. What does if and only if mean? Well, what that means is if this first property is true, then the second is true. In other words, if the length of some vector equals 0, then you know that vector must be the 0 vector. Okay, but it also means it goes in the other direction. It means if you start with the 0 vector, then its length equals 0. In other words, if and only if, this terminology here, it means that these two things imply each other. They are equivalent to each other. Okay, and hopefully this makes some intuitive sense. Yeah, the 0 vector, it has length 0, right? It sort of doesn't point anywhere, it just stays at the origin. And every other vector has some positive length, some non-zero length. Okay, so the 0 vector is the only one with length 0. And so let's prove these properties here. Let's see how we algebraically prove them. Even though they're clear geometrically in 2 and 3 dimensions, I mean, we want to be sure that they're true in higher dimensions where we can't really picture things as well. So let's prove these. All right, so to prove property A, we just sort of plug everything into the relevant definitions, and everything just pops out exactly how we would want it to. Okay, if we want to compute the length of c times v, well, it's just the square root of the dot product of that vector with itself. That's the definition of vector length. Okay, and now, well, I've got a dot product here with some scalars in it, and one of my properties of the dot product said, hey, you can pull those scalars out in front. So I'm going to pull this c out in front, I'm going to pull this other c out in front, and when I do that, now I'm going to have a c squared out in front, right? I pulled 2 copies of c out in front. Okay, next thing I'm going to do is just properties of real numbers and square roots, right? I've got a square root of a product of 2 real numbers, c squared and this dot product. So I can just split that up into the product of 2 square roots. All right, and then the last thing I'm going to do is I'm just going to simplify these 2 terms here. Square root of c squared, well, another way of writing that is absolute value of c, right? If you square and then square root, well, that does nothing, except it throws away the minus sign if there was a minus sign. In other words, it does the same thing as absolute value. And over here, I've got square root of v dot v. Well, that's exactly the definition of the length of v. Okay, so just make those 2 substitutions and we get absolute value of c times length of v, which is exactly what we wanted. All right, next up, we want to prove property B. Okay, and property B was this funky little if and only if thing. Okay, so I want to be a little bit careful here because if and only ifs are sort of new to us. If you want to prove an if and only if statement, you have to prove 2 things. You have to prove it in both directions. You have to prove that if v is the 0 vector, then its length is 0. Okay, so that's one thing that we've got to prove. But we've also got to prove another thing. We've got to prove that if the length of a vector equals 0, then it must be the 0 vector, okay? Because it's if and only if, you got to prove it both ways. Okay, and what very often happens with if and only if theorems like this is very often the proof of one direction is very, very straightforward, and then the proof of the other direction is the real pain. That's sort of where the meat of the proof is. Okay, so in this particular case, the easy direction is going to be this first one. It's going to be number 1. If it's the 0 vector, then it has length to 0. So let's see why that is. Well, just plug into the definition. If I'm working with the 0 vector, then the length of v, well, that's the length of the 0 vector. And what is the length of the 0 vector? Well, the 0 vector has every one of its entries equal to 0. So the way I compute its length is I do first entry squared, well, 0 squared. Second entry squared is 0 squared, and so on. I'm adding up a whole bunch of 0 squareds, and then I square root at the end of the day. Well, of course, that's going to get me 0. Okay, so yeah, the length of the 0 vector does equal 0. So yay, check mark, we're happy with that. That is all that's required for the proof of statement 1 here. Okay. So the rest of this is going to be the proof of statement 2. I want to show that if I compute the length of some vector and get 0, then I know I must be working with the 0 vector. So how do I do that? Well, start off with my assumption. Start off with, well, if the length of the vector equals 0, what does that tell me? Okay, well, what it tells me is, again, I'm going to just use the definition of vector length here. What is vector length? Well, it's this funny little formula here, right? Add up the squares of the entries and then square root at the end of the day. I know that quantity's got to equal 0. Okay, and a little sidebar before we go much farther here. This notation here might be new for some of you. Okay, what this little arrow here means, that's called an implication arrow. Okay, and all that means is this thing over here, it follows logically from this thing over here. In other words, this implies this. Okay, so if this is true, then this is true. That's all that arrow means. All right, well, but if this is true, then I can square both sides to see that this is true. So again, the implication arrow just means that this statement over here follows from this statement over here, okay? And the way that it follows is just from squaring both sides. Okay, and now I look at this expression over here. And what do I have? Well, I have some number squared plus some number squared and so on, plus some number squared equals 0. But what do I know about the square of numbers? I know that each of them is bigger than or equal to 0, right? v1 squared is bigger than 0 because it's something squared. And similarly, v2 is bigger than or equal to, sorry, v2 squared is bigger than or equal to 0, and so on, all the way up to vn squared is bigger than or equal to 0. All of them are bigger than or equal to 0. So the only way their sum can actually equal 0 is if each of them equals 0, right? Because if even one of them was not equal to 0, then that sum would have to also be bigger than 0, right? Because you'd be taking something positive and adding non-negative jump to it. It would still be strictly positive. Okay, so the only way that sum can equal 0 is if each of the individual terms, v1 squared, v2 squared, and so on, if all of those equal 0. Okay, and then you just take the square roots of each of these, okay? And you see that, oh, v1's got to equal 0, oh, v2's got to equal 0, and so on. In other words, you're working with the 0 vector, right? All of the entries are 0. Yeah, that's the 0 vector. All right, and then that's the whole proof, okay? Then we're done. Okay, so now that we understand basic mathematical properties of vector length, let's do something with it to round out this lecture, okay? And that thing that we're going to do is we're going to introduce unit vectors, okay? And all unit vectors are they're vectors with length 1, okay? So if you look at some vector and it has length 1, great, it's a unit vector. If it doesn't have length 1, it's not a unit vector. That's all there is to it. But sort of the interpretation of unit vectors is they specify a direction in space, okay? So every direction in space, it has a unit vector pointing in that direction, but moreover, it has exactly one unit vector pointing in that direction. Okay, so we think of unit vectors as specifying a direction. Okay, and then the nice thing is that every vector, or at least every non-zero vector, can sort of be split up into two components. It can be split up into its length and its direction. In other words, a length and a unit vector specifying which direction it's pointing in. Okay, so how do we do this? Well, what we do is for every non-zero vector, you can take that vector and divide it by its length. And when you do that, you get a unit vector, okay? So if you take any non-zero vector and divide it by its length, you get a vector that has length 1. And the reason for this is, well, let's just compute it and see why this happens. So suppose that you've got some vector v that, that's your vector v that you actually care about. And then what we're gonna do is, I claim that this vector w, which is v divided by its length, I claim that's a unit vector. Okay, so how do we see that? Well, just compute its length. Compute the length of w. Okay, and when we do that, okay, great, the notation's kind of ugly, but you just slap length bars on both sides of that expression there, and then you get this ugly expression here. Now I'm just going to rewrite things a little bit, right? V divided by length of V, another way of writing that is 1 divided by length of V times V. Okay, and the reason that I'm doing this is I like thinking about things in terms of scalar multiplication rather than scalar division. Like, of course, they're sort of equivalent in this sense, like one is just 1 divided by the other, but I just want to be a little bit careful here. So I'm thinking of V divided by the scalar, well, that's the same as 1 divided by the scalar times V. Okay, and then, well, one of my properties of vector length that I just proved right up above says, hey, if you've got a scalar inside these length bars, you can pull that out in front, right? Scalar multiple of a vector, well, the length of that is just, you pull the scalar out in front. So I'm just going to pull this 1 over length of V out in front, and then I'm just left with length of V itself inside the length bars. Okay, and then, of course, these guys just cancel. These are real numbers now, right? Length of V divided by length of V, I just get 1 at the end of the day. So yeah, W has length 1, so W is a unit vector. Okay, when we do this, when we take a vector and we scale it to have length 1, that's called normalizing the vector, okay? Rescaling to have length 1 is called normalizing, and I mean, the rescaled vector is sometimes called the normalization of the original vector. And the idea there, the idea behind this is that this vector W, it tells us about the direction of V, okay? It tells us what direction V is pointing in, but it doesn't tell us anything about the length of V. All right, so let's just do a quick example to make sure that we understand normalization. So suppose that you start off with this vector 3, 4, okay? Let's normalize it, okay? And all that means is rescale it so that it has length 1. Okay, so first thing you've got to do is you've got to compute the length of that vector, right? Because you want to divide by the length. Unfortunately, we already did this calculation earlier. The length of that vector, we saw that it equaled 5, okay? This is the very, very first example of computing the length of a vector that we did earlier in this lecture. Okay, so then to normalize the vector 3, 4, all you do is you divide by 5, okay? And that's really all there is to it. The normalization of 3, 4 is the vector 1/5 times 3, 4. And if you like, you can pull that 1/5 inside, so the entries here are 3/5 and 4/5. Doesn't matter, same thing, okay? Geometrically, what's going on here is we started off with this vector 3, 4 that points over 3 units and up 4 units, and we rescaled it so that it's on the unit circle, right? If we draw the circle with radius 1 centered at the origin, then this rescaled vector 1/5 times 3, 4, that vector is exactly there, right? It points in the same direction as 3, 4, but it's shrunk down so that now its length is 1 and therefore is on the unit circle. Okay, so that's all we did when we renormalized. We shrunk it down so it's on the unit circle. Okay, another quick example just to make sure that we understand the concept here. Let's show that the standard basis vectors are unit vectors. So first thing I'm going to do is, well, let's remind you of what the standard basis vectors are. We introduced these last week, and remember there are these funky vectors that we denote by EJ, so like E1, E2, and so on. And what they are is they have zeros in all of their entries, except there's a single 1 in one of their entries, and that's denoted by, you know, whatever the subscript is. So whatever J is, that tells you where the 1 is in this vector. So E1 has a 1 in the first entry, E2 has a 1 in the second entry. In general, EJ has a 1 in the jth entry, and zeros everywhere else. All right, so let's show that each of these guys are unit vectors. All right, so just compute the lengths and show that the lengths are 1, right? That's all that it's asking, okay? So the length of EJ, well, let's just take the entries, square them, add them up, and square root at the end of the day. So you get a bunch of 0 squareds added together, and then in the jth spot, you get a 1 squared. So of course, this is just square root of 1, which is just 1. Okay, so yeah, that vector has length 1, and that's all there is to it. So each of these vectors, they live on the unit circle or sphere or hypersphere in higher dimensions. Okay, and that will do it for today's lecture, so I will see you next class when we start looking at more... Okay, so that'll do it for today's class. I will see you next lecture when we start looking at sort of more surprising properties of the length of a vector. Okay, so I'll see you then.